Hey there, Algebra 1s. I see you have some graph paper there. You must be plotting something. This is our video about the coordinate plane and using graphs to relate to quantities. Let's start with the coordinate plane. Okay, the coordinate plane was designed by, or I guess developed by a guy named René Descartes. 17th century French philosopher and mathematician, also famous for the quote, "I think, therefore I am." Basically saying if we have consciousness, we must exist. Well, of course we exist. You're right there. I can see you and feel you and, pat you on the head, whatever. But apparently in the 17th century, that was kind of a revolutionary thought. Anyway, he developed the Cartesian coordinate system, but we actually had it before that. Map makers in ancient Greece had a coordinate system long before that. So when we talk about a coordinate system, we're talking about the system that actually lets us, let's see if I can draw a kind of a crappy United States, and then a South America down there. Oh, that looks awful. Anyway, we had a coordinate system already because we used it to navigate. We use it to navigate and make maps and locate things. So the coordinate system is the first link between algebra and geometry. Taking the abstract concepts in algebra, took the abstract and made it something more concrete and visual. Okay? That way you can apply it to things in the real world. Okay? Old coordinate system with our definitions. Everything here you need to know. Everything you need to know is on the screen. The x-axis and the y-axis, together they're called axes, the x and y axes. The origin, is 0, 0 here in the middle. Let's put a little ordered pair, origin, 0, 0. The four quadrants, 1, 2, 3, 4. Remember that it goes counterclockwise, 1, 2, 3, 4. And when you say the x and y coordinates of a point, for example, point B would have the x and y coordinates negative 3, 4, like you see up there. Those are the coordinates right there. And the old school words for those are the abscissa and the ordinate. The abscissa and the ordinate. You never know, I might use that for a bonus question or something, because that is kind of a cool vocabulary to know. So you've got to know all of that. Let's look at some of these points here. Why don't you go through real quick, pause your video, and write out what the ordered pairs are for all these points, just to make sure you remember how to find them. Make sure you've got it straight. F and G. And I'm going to go ahead and start writing them. So if you don't want to see these answers, pause it and do it yourself. So A, start your origin, positive 5, positive 3. So that point is 5, 3. B, negative 3, positive 1. So when we're looking at the points, if we move to the left on x, that's negative. The right on x is positive. Up on y is positive. Down on y is negative. C, negative 6, negative 4. D is on the y-axis. So negative 0 for x, because we're not moving right or left, and negative 3 for y. So 0 for x, because I didn't move right or left, and negative 3 for y. E is right at the origin, so that's 0, 0. F, positive 4, negative 5. And G, right, is positive 6.5, or if you will, positive 6.5. But you don't go up or down, so 0 for the y coordinate. Not hard to do. Graph, 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 not hard to do. So now we're going to get into talking about using graphs to show relationships between two things. When we talk about using a coordinate plane, a graph to show a relationship, we're making a visual representation of a relationship between two quantities as they change. We can use tables and graphs to show relationships between variables. Your x coordinate and your y coordinate have other values when you're talking about these kinds of situations. Your x is your good old independent variable. Just like science, we have an independent variable, and that is the x. The y is the dependent variable. The dependent variable is the y, the independent is the x. Think about it like this. In pre-algebra, when we gave you y equals 2x minus 7, when you then made a table, did you provide the x's or the y's? You provided the x's. So your input was the x's. So that's another word we can use for this. Input. And what came out was the y's. output. We can use a graph to show different situations. So take a look at this. Which graphs relate the height of the water to the volume of the water in each container? Which graph goes with which container? Justify your reasoning. So we're going to go ahead and do this now. So in one graph, you've got the volume is going up at a steady rate, and then it kind of drops off. So as the volume is getting higher, the height is not getting as high as fast. On this one, it's your height is not going up that far, and your volume is increasing at a steady rate. Here, your height is going up much further, and your volume is increasing at a steady rate over the height of the container. Or the height is increasing over the course of filling the volume of the container. So I don't think you're going to find this super difficult. Take a second and match them up. And now I'm going to do the same thing. This one that kind of slows down, this has got to be C. It's got to be C. This guy over here, just in case you can't see the color. Because it would fill steadily, and then it will continue to fill, but the rate of the height won't go up as fast. Because as it fills, you're getting more volume filled through this part of the height. It's just the volume is continuing to go up, but not as fast as the height was going up before in here. So that's got to be C. All right, and then the other two are super easy. This one's got to be A, because it doesn't have super high height. It's just not that high. It's nice and low, nice and low. And then B, which is this one. Because you've got, again, the volume fills steadily at the same rate all the way till you get to the top, but it's got a higher height. So you can take a graph and show a situation just like that. Let's try another one. This graph shows the volume of the air in a balloon as you blow it up until it pops. What are the variables? Describe how the variables are related at various points on the graph. Okay? Well, our independent variable is the time, and our dependent variable is the volume. So what's happening at first? Well, at first, the balloon is being filled steadily. So you take a breath in and you blow into the balloon, and then you run out of breath. And then you stop and you pinch the balloon shut, and the volume is not changing. And you take another deep breath in and you blow into the balloon. And you run out of breath, and you stop and you pinch the balloon, and you take another breath in. And you blow up the balloon. And you take another breath in, and then you blow up the balloon, and it got too big, and pop. So what's actually happening here is all of these points, all of these sections, so blowing air into the balloon. But all of these points changing colors, all of these points, that's when you stopped to breathe. And then finally, at the end here, what's that? What's this? Okay, balloon did what? Yep, I heard somebody say it at home at their house. The balloon popped. No, of course I can't hear you. And it would be truly disturbing if I could. But anyway, that's how we take that information and we can interpret what was happening. Or we can sketch our own graph. A model rocket rises quickly, then slows to a stop as the fuel burns out. It begins to fall quickly until the parachute opens, after which it falls slowly back to Earth. What sketch of a graph could represent the height of the rocket during its flight? Label each section. Okay, so we got to start by thinking about what our graph is going to look like. Well, what's happening on the x-axis? What's the independent variable here? It's the passing of time. It's the passing of time in seconds, because model rockets happen fast. If you didn't watch the news and see about Wallops Island last week or earlier this week when the rocket blew up, it happens pretty darn fast. And then what are we comparing it to? Well, we're comparing a graph that's the height over time. So this will be the height over here. And I would assume that we'd be talking about probably the height in feet. So the rocket launches and it rises quickly. But then over time, it gets to a peak and then it runs out of fuel and it starts to fall and then poof, the parachute opens. And you get a steady decline down towards the earth. So you get the point where it rises quickly to begin with. So it's rising quickly to begin with. Okay, so this is the launch. Okay, it rises quickly. And then after that, what happens next? Well, you've got, it starts to fall quickly, but the parachute opens right there. So the chute opens, and the rocket then falls steadily back down to Earth and hit the ground. So you can describe what was in this with a graph. So comparing time, height over time, launch, runs out of fuel, starts to fall quickly, chute opens, and it gently falls steadily down to Earth. Okay? All right, so you now have an idea of what we're trying to get at when we say relating to quantities with a graph. Let's take a look at a few more examples. I'm going to have you try on your own, and then we'll go over them. Okay, so you got 4 problems to look at. I want you to pause them. I want you to try it. See what you can do on your own, see what you understand on your own, and then we'll be going over it in the video. So pause your video, please. Okay, I know some of you probably won't, and that's okay. But let's go ahead and actually go over these. What are the variables in the graph at the right? Use the graph to describe how the variables are related. Well, in number 1, the independent variable would be, remember that's your x, car weight. Because that's what's changing. That's the changing variable. The dependent variable depends on what the independent variable is, and that's the fuel used. Well, can we describe what's up here? Okay, as cars get heavier, what happens? As they get heavier, they use more fuel. If you drive let's see, a Volkswagen Beetle or a Mini Cooper, you're not going to use as much gas as if you drive a Tahoe or a minivan or a Hummer. All right, the heavier the vehicle, the more gas it's going to use. Let's do the next one. Describe the relationship between time and temperature in the table below. Time in hours, so the hours go up by 2, 4, 6. So it's every 2 hours, afternoon, the temperature in degrees Fahrenheit. So over the course of the day, okay, as time passed, what happened? Well, the temperature went up, the temp increased, then decreased. And that should make sense. Because, you know, we live in Virginia, so you know in the summer there are times of day where it's so brutally hot out that you can't even leave your house comfortably. And that would be like 1, 2 o'clock in the afternoon. So think about this. So as the time got later, so afternoon, 1 hour afternoon, it was 61. Now, clearly this is not brutally hot, but it's the same behavior that the temperature has during the winter and fall months as it has during the summer months. So you've got the temperature is increasing and then begins decreasing after that. All right, number 3, match one of the labeled segments in the graph with each of the following verbal descriptions. Rising slowly, constant, and falling quickly. Well, rising slowly would be B. Rising slowly would be B because it's not steep. It's not steep at all. Think about if you tried to ride a bike up this, it'd be very challenging. Up this would still be challenging, but not as bad. And then we have constant. Where would it be constant? Where would it be constant? Constant means staying the same. Being constant, staying the same. That's C because it stays flat. Stays flat, constant. And then falling quickly. Where would we find falling quickly? Well, that would be D. D is where it's falling quickly, because you can see it has a downward trajectory going downwards, and it's going down fast. Falling slowly for E, but we didn't have that. Rising quickly for A, but we didn't have that. And there you go. Describe a real-world relationship that could be presented by the graph sketched above. So this is where you get to be fun and creative about it. So what could this show? Well, it could show a mother bird taking off from her nest, and she's rising really, really quickly when she gets up to a certain point, and then she doesn't quite rise as fast because it's starting to get cold up there. The air is kind of thin, and then she stays at the same height for a while. And mother bird is out there looking for cute little squeaky mice to get for her baby birds, and she's going to tear them into little bits and feed them to her baby birds. Sorry, I know it's gross, but nature is pretty gross. Darn nature, you gross. All right, so what's happening here? She's staying up at a certain height, and then she uses her super, super awesome mama bird eyes to see a critter in a tree. It's a chipmunk. It's either Chip or Dale. Who cares? But it's about to get eaten. And she dives down real fast. And she catches the little chipmunk, and then she goes down slowly. She falls slowly. Well, not falls, but flies slowly back down, almost to the ground. So in my scenario, gotta get the writing tool to write. This is time, and this is mama bird's height. And look, she didn't get all the way to the ground. She's not all the way to the ground. She's maybe in a tree with the nest, with the baby birds, ripping that little chipmunk thing to shreds so she can feed her babies. Again, nature is gross. So I bet you had some interesting ideas for that one. If you did, I want you to bring them in. I would like to hear them. And I will see you guys after your day break in class.